Every day you hear claims like, "This supplement changed my life," or "Experts say this works," or "Studies prove this is true." But the problem is simple: not all evidence is equal. Some of the things that sound the most convincing are actually the weakest forms of evidence we have, while the strongest evidence is often the least dramatic. In this video, we're going to walk step by step through the entire hierarchy of evidence, from personal stories at the bottom to meta-analyses at the very top, so you can understand which claims deserve your trust and which ones you should question. Not all evidence is created equal. Some types of evidence feel incredibly convincing, a dramatic story, a confident expert, a viral TikTok. And yet, scientifically, these are the weakest forms of evidence we have. Meanwhile, the strongest evidence, large studies, systematic reviews, meta-analyses, often feels dry, boring, and disconnected from everyday experience. So today, we're going to walk through the entire hierarchy of evidence, from the weakest to the strongest, and see why some evidence misleads us, while other evidence helps us get closer to the truth. Once you understand these levels, you'll never look at health advice, scientific claims, or studies show headlines the same way again. Let's begin at the bottom: anecdotes. Anecdotes are personal stories. Someone says, "I tried this diet and it cured my illness," or "My cousin took this supplement and it changed their life." These stories feel powerful because they're emotional. They involve real humans, real feelings, and real drama. But scientifically, anecdotes tell us almost nothing. Why? Because they're full of hidden variables. Maybe the person improved for reasons unrelated to the treatment. Maybe they would have improved anyway. Maybe they're biased, misremembering, or exaggerating. Maybe they're just one of the lucky few. Anecdotes are compelling because the human brain loves stories. But they're the weakest form of evidence because they have no controls, no comparisons, and no way to isolate cause and effect. Now let's go one step higher. Expert opinion. Expert opinion sounds impressive. A doctor says it, a professor says it, a scientist says it. Surely that must count for something. And it does, but not as much as you think. Experts can be brilliant, but they're still humans. They can be biased, influenced by trends, limited by the information they've seen, or simply wrong. Expert opinion is helpful when we have no strong data, but evidence-wise, it's still very low on the pyramid. Next, we step into early scientific observations, case reports, and case series. Imagine a doctor treats a patient with a strange symptom and thinks, "This is unusual." They write a report describing that single case, or a series of patients with similar details. This kind of evidence is useful for discovering new patterns or identifying emerging diseases. But it cannot prove causation. It can only say, "This happened and we noticed." Now let's move to cross-sectional studies, where researchers collect data from many people at one moment in time. For example, do people who eat more vegetables have better heart health? These studies can find correlations patterns in the data, but they cannot say which direction the effect goes. Maybe vegetables improve health, or maybe healthy people tend to eat more vegetables. Cross-sectional studies can't tell. Next up are case control studies, where we compare two groups, one with a condition and one without. For instance, we compare people with lung cancer to those without and ask what's different between them. These studies are useful because they help identify risk factors, but they can be misleading because they rely on memory assumptions and indirect evidence. Now, we reach a stronger type cohort studies. In a cohort study, researchers follow a large group of people over time. They track what people do and what eventually happens to them. For example, follow smokers and non-smokers for 20 years and see who develops cancer. This gives us stronger evidence because we observe changes over time and can see potential cause and effect pathways more clearly. But cohort studies are expensive, slow, and still vulnerable to confounding variables factors we didn't measure that might influence the results. Now, we reach one of the strongest forms of evidence, randomized controlled trials, or RCTs. This is the gold standard for testing treatments. People are randomly assigned into two groups. One gets the intervention, the other gets a placebo or standard treatment. Because the assignment is random, these studies can isolate cause and effect with far greater clarity. RCTs reduce bias balance, confounding variables, and provide the cleanest comparison we can get. But even RCTs aren't perfect. They can be too small, too short, too narrow, or not representative of the real world. So what's stronger than an RCT combining many RCTs? Now we reach the top of the evidence hierarchy: systematic reviews and meta-analyses. A systematic review gathers all studies on a topic, filters out low-quality research, and synthesizes the results into a clear overview. It fights publication bias, cherry-picking, and selective interpretation by using rigorous criteria. A meta-analysis goes even further. It actually combines the data from multiple studies into one massive superstudy, increasing statistical power and reducing uncertainty. Meta-analyses are the closest thing we have to the scientific truth on a topic, not because they're perfect, but because they pool the strongest available evidence. So from weakest to strongest, the hierarchy looks like this. Anecdotes expert opinion case reports, cross-sectional studies, case control studies, cohort studies, randomized controlled trials, systematic reviews, meta-analysis at the top. But here's a twist. Even the strongest form of evidence can be wrong. Why? Because science is a moving process. Meta-analyses can include flawed studies. Publication bias can distort the data. New discoveries can overturn old conclusions. And sometimes the territory reality is more complicated than our models can capture. So understanding the levels of evidence doesn't mean treating high levels as absolute truth. It means knowing how much confidence to place in a claim and where it sits on the ladder of reliability. Now let's talk about how this applies to real life. When you hear someone online saying, "This cured me," ask yourself, is that anecdote or evidence? When you hear a confident expert saying, "In my experience," ask, is this opinion or data? When you see a headline claiming, "Study proves," look deeper. What kind of study is it? Is it observational, correlational, a randomized trial? Or is it a meta-analysis combining dozens of trials? Understanding levels of evidence helps protect you from misleading claims, magical cures, sensational headlines, and viral misinformation. It helps you think like a scientist, even if you're not one. It helps you understand that the strength of evidence grows as bias shrinks, that the more controlled and rigorous a study is, the more trustworthy its conclusions become. And it helps you navigate the modern world, a world full of claims, opinions, and data with clarity and confidence. At the bottom of the evidence pyramid are things that feel true. At the top are things that actually help us get closer to the truth. Anecdotes feel powerful. Meta-analyses are powerful. And once you understand how evidence is built layer by layer, you can finally separate noise from knowledge, stories from science, and belief from reality. If this breakdown helped you understand why some types of evidence are trustworthy and others are misleading, remember, this evidence becomes stronger as bias becomes weaker. Anecdotes feel powerful, but meta-analyses reveal the truth. If you want more videos that turn complex scientific ideas into clear, simple stories, make sure to subscribe, leave a like, and tell me what topic you want explained next. Thanks for watching Plain Explain, where better thinking begins with better understanding.